Swayam Prabha. Digital India. Educated India.
Dear students, now that we are familiar with both primal and dual approaches for optimization, let us move to a very important concept in infrastructure planning and management that would be quite handy many times, which is integer programming. So, in this lecture, we are going to discuss why integer programming matters in infrastructure, or why integer decisions are important when we talk about infrastructure systems. We will also do a quick recap that what simplex and linear programming gave and what is going to be different in integer systems. Then we will go into more formal introduction to integer programming, where we will discuss these challenges of fractional optima and how to handle them. We will introduce an idea called as branch and bound method as applied to integer programming, and we will illustrate all these concepts with help of couple of examples. One example would be very straightforward and another would be somewhat more complex when it comes to integer programming, and finally we will conclude and discuss what are the future next steps that we need to take in the context of reinforcing the concepts that we learn here. So, here is a very simple example in the context of infrastructure systems. Let us say that you are planning to buy certain resources for your large scale project. Now, at the end of your exercise, you see that you are optimizing certain resources where x1 happens to be number of cranes you may have to get, and x2 are number of trucks you have to employ at particular sites to get maximum profit out of your project. Now, you solve the entire optimization exercise. You might have used primal method, you might have used dual method. Mathematically, you are very robust, but at the end you saw that your answer is, let us order 2.7 buses, 3.4 trucks, or 2.7 cranes, or 3.4 trucks, and so on, and it does not make any sense, because you can either order 3 trucks or 4 trucks and so on. So, while your answer is optimal, it is not practical for implementation, because you would only expect the integral solutions or solutions that are numbers, discrete numbers 1, 2, 5 and so on. And that is the way, that is where the name integer programming comes into picture, that for same set of the problem where you have objective function, where you have constraints, only integer answers are acceptable. So, once we are done with this integer programming exercise, we would notice that integer programming forces discrete decisions that match reality, because LP solutions are often fractional values, because there is no constraint in linear programming to produce the non-fractional, just produce non-fractional or integer answer. Now, a very quick recap of linear programming. We were dealing with problems of maximization or minimization type. Problem was maximize C transpose x subject to Ax less than equal to B, where x was greater than equal to 0. This is a linear programming problem stated in its standard form. What we learned in linear programming introduction is that whenever your all constraints are of linear type, the region that they would bound is always going to be convex, and sometimes we call this particular region, this convex region, as convex polytope. What I am highlighting here is one simple polytope. As you see that this region is convex, I take any 2 points within this region, join them by straight line, the line is always going to stay within the region, and that is the definition of convex polytopes that we learned. And we learned that we will be moving from one extreme point to another extreme point when we were talking about linear programming. Now, the extreme points of this convex polytope can be something like 3.4 comma 2.4. This point can be 4.5 comma 1.5. This point can be 0 comma 0. This point can be 2 comma 3.5 and so on. I have just written these values not to scale, so don't get confused how one point is higher and so on. But the point that I am trying to make here, although all these points are at the extrema, only 0 comma 0 qualifies to be an integer solution, but as you can see this happens to be a trivial solution which is of no value to us, and all other solutions that any linear programming problem or a dual problem will give is going to be not so useful for us because it is not practical. And that is where integer programming problems are harder to solve in comparison to linear programming problem because of their invalidity in practice. The linear programming solution that we get may be invalid in practice. To convert that invalidation into something practical form is the biggest challenge associated with integer programming, and we will learn a trick to do that in this particular lecture. So, whenever we state an integer programming problem formally, the constraints and objective function remains the same. However, additional constraints come around the variable x itself. If you recall, in linear programming, we were simply writing x greater than equal to 0. Now, x has to be greater than equal to 0. In addition to that, x has to belong to z space or integer space, and there is no way to account for that in default linear programming problem. Again, bolstering my earlier point, that makes integer programming problems a bit difficult to solve using simplex construct, because original simplex method never spoke about how to discard or accept a particular solution, because it would keep feasibility at a core for the original problem where x was greater than equal to 0, and that is where deviation will occur. So, why is it specifically harder? Is that we may have to search among discrete points which are possibly huge in number. So, for example, if I take this polytope and I put a grid around this like this, now this grid can be of any resolution, and if these grid points are the points that are representing integral space within or at the intersection of this convex polytope, in 2 dimension I can still go from one point to another point and so on. But when I talk about multi-dimensional problem, number of these feasible integer grid points may be very, very large. So, checking for all these particular points may become computationally very expensive, and hence not so pragmatic to find the optimal solution. So, we have already seen that while LP is easy to solve, the optimal corner point is a non-integer, and I will again illustrate this point with help of an example. Let us say that we have a problem of nature maximize x plus y, and it is subject to constraint x plus y less than equal to 5.5 and x and y are greater than equal to 0. Now, this is a very simple problem. If you talk in linear programming space, you can easily, in this problem, like solution is so obvious, you don't even have to go to simplex method. But for sake of simplicity, what I would say is that I go through entire simplex exercise, and after all my tableaus are done, I will get to one particular value. So, x may come out to be 3.5, y may come out to be 2.5, or x can be 2.5 and y can be 3.5. Both of them will give me an answer of 5.5. So, that is of course a feasible solution, that is also an optimal solution, and there is no better solution than that because this is simply the linear sum. I can also say that x equal to 5.50, there are infinite number of possibilities. So, let us try to understand this with help of an example where we have this problem, which is a very straightforward problem, that x plus y is less than 5.5, xy greater than equal to 0, and problem is of maximization type of maximize x plus y. Prima facie, this is such a straightforward problem that you would not even need simplex W to solve this, but for sake of consistency, let us say that we solve this entirely through one of the optimization methods, and at the end we find that x is equal to 3.5, y is equal to 2.0, or x equal to 2.0, y is equal to 3.5, or there are infinite solutions possible, as you can imagine, because this is along the straight line and whatever values are less than that are part of the feasible solution. Now, the problem here is that if you are exactly on that line, none of the solutions are acceptable if you are talking about integer programming, because both x and y has to be integers. Now, if any of them ceases to be an integer, let us say I say that x is equal to 2.5, y can still be forced to be 3, yes, y is an integer, x is not an integer, but my primal or basic feasible solution is no longer feasible anymore. It was feasible in primal space, but not feasible in the integer space, and that is where I need some methodological approach to deal with that. So, the LP optimal, all are fractional solutions if they are exactly have to be on the bound, and when x and y are restricted to integer space, none of them ceases to be the valid solution, and that is where a methodological approach called as branch and bound method comes into picture. There are many ways, by the way, to solve this integer programming problem, but I would not go into details of all methodologies. Those who are interested in concepts of optimization from the theory side should definitely explore this excellent book by Rao on engineering optimization that lists multiple such methods to solve integer programming, but this one makes lot of sense from the engineering side, and we will also see how to put it into practical use by solving couple of examples. So, how branch and bound method works, let us take an overview. So, what we will do, we will first solve the linear programming problem as if we are solving it for x greater than equal to 0, that is, we will ignore the integrality constraint. All solutions we will assume are going to be acceptable as long as they are basic feasible solutions, and basic feasible solutions here are in the context of simplex W only. Sometimes you may be very lucky that you solve a simplex W and all solutions that you get are integer by chance. You are done. That is going to be the most optimal solution and nothing is needed to be done from there. However, in most of the cases, you may not be that lucky that by default you are ending up on integer solutions, and that is where branch and bound method will come into picture. So, what branch and bound method would do is that, let us say that you solved for various variables, you got x equal to 2.0 and y is equal to 3.5. In bound method, branch and bound method, you would say that, now I cannot live with this optimality of y equal to 3.5. I have to find whether y is less than 3 or y is greater than 4. I will split it into two branches and see that on which side of 3.5 I should go, so that my objective function is maximized if it's a maximization problem, or minimized if it's a minimization problem, while making sure that y is bounded to be an integer, or there is a bound here, there is a bound here, this is the lower bound and this is the upper bound, and then we will introduce this as an additional constraint into our original optimization problem, and we will solve two branches now. One with original set and one additional constraint coming from branch A and another set coming from branch B, and we would say that now we have splitted this problem into two sub problems, and sometimes we also call it as a search tree. Now, once we solve one particular tree, we may see that one branch is feasible or less optimal than the other. We would keep on pruning or cutting those branches off from our solution, and we will continue until all branches are pruned and yield integer solution. So this is a very systematic way to find a global optimum among discrete points rather than searching haphazardly or in hit and trial mode across all the possible integers that are at the extreme points of our polytope or nearest to the polytope. So again, going back to our very simple example, we will see this branching here in this simple example, and then in a more realistic example where both x and y happens to be non-integer solutions in our original simplex tableau. So here is a problem, same problem, x plus y less than equal to 5.5. This is a maximization problem. In addition, there are two more constraints, that x has to be greater than equal to 2, y has to be greater than equal to 2, and then there is an integer constraint. So first of all, what we will do is that we will ignore this particular constraint in our first step of branch and bound method and solve the problem, which is simply maximize x plus y subject to x plus y less than equal to 5.5, x and y belongs to greater than equal to 0. We can solve it using simplex tableau, and as we discussed, we may get answers as 2.53, 3, 2.5, 2.4, 3.1. You see that all the values less than zeros do not exist anymore because there is a boundation of x being greater than equal to 2 and y being greater than equal to 2. But you can see none of them are integers if x plus y is equal to 5.5. So one thing is clear, that we will settle for some value of x plus y less than 5.5. Another thing that is clear in this toy example, that we will most probably settle for the solution which is x plus y equal to 5. But in real problems, this kind of intuition may not be there, so it's important to focus on the methodological details. So what we do here is that when x plus y is less than equal to 5, based on our earlier discussion, we can explore certain points 2, 3, 3, 2, 5, and maximum integer value that is going to come out to be 5 in this example. However, if I go by the branch and bound method, which is more generalizable, I will put branch on y equal to 2.5. I will say that either y is less than equal to floor of 2.5 or y is greater than equal to ceiling of 2.5, which happens to be 3. And each branch itself is a smaller linear programming problem with an added constraint on y. So this will become branch A and this will become branch B. Now I will solve this sub problem A where y is less than equal to 2. You see, this was my original constraint, this was my original constraint, this was my original constraint. This is the added constraint from branch A. And then I simply solve this particular problem. I get the solution as 3, 2 or z equal to 5, which is feasible as well as integral. Now I will do the similar problem with sub problem B, where I will say that x plus y is less than equal to 5.5, x is greater than equal to 2. Now I need not write y is greater than equal to 2 because this becomes a redundant constraint because of the branching that I took, which automatically says that y is greater than equal to 3. So again I solve this, again I get this answer as 2, 3, z equal to 5. Again this is feasible and integral. So branch A yields us z equal to 5, branch B yields us z equal to 5, both of them are acceptable solutions, both of them are integral solution. So this IP optimum is indeed 5 with multiple integer solutions, which should have been the case if we would have gone by the obvious calculations. Now let us solve one more interesting example, which is bit more involving than our original examples. So here the question that we are given, again I am borrowing this particular example from engineering optimization book by S.S. Rao, and readers are encouraged to refer to that particular book if they want more insights into the methods of linear programming, and it would be much easier to follow after this particular lecture that what various theoretical approaches are taking us to. So here the problem that we are dealing with is a maximization problem. Maximize f equal to 3x1 plus 4x2, and it is subject to constraint 7x1 plus 11x2, and this is less than 88, and next constraint is 3x1 minus x2 less than equal to 12, and x1 is greater than equal to 0 and x2 is greater than equal to 0. Now there is another constraint that xi belongs to z and all of them have to be positive. So as we discussed earlier, our first approach would be that we will treat it as a simple. Step 1 would be treat it as simple optimization problem with xi equal to z plus ignored, but xi greater than equal to 0 followed. The moment we do that, this can now be solved using this simplex method, which gives us the solution as xi equal to 5.5. I am not going to solve the simplex tableau here, but this is for users to solve this example themselves using pen paper or some programming language or simplex tableau, but this is what you should get when you solve with the constraint relaxed. Now if this is clear, do you see the problem here that xi is equal to 5.5, x2 is equal to 4.5 and f star is 34.5. Neither x star 1 is integer nor x2 star is integer. So what we will do? We will do first branching. And as we said, first of all, we will go behind x1 and we will put two conditions on x1. First condition would be that x1 is less than equal to 5, and second condition is that x2 is greater than equal to 6, not x2, x1 is greater than equal to 6, and it follows the same logic that if since we are having 5.5, we will take x to ceiling 6, x to floor 5 and look for solution on either side except that particular domain where it is having the fractional value. Now when x1 is greater than 5, we will have two branches coming out here. So I will just write branch 1 and branch 2. So branch 1 would look like maximize f equal to 3x1 plus 4x2 subject to 7x1 plus 11x2 less than 88, 3x1 minus x2 less than equal to 12, an additional constraint of x1 less than 5 and x2 greater than 0. Similarly, branch 2 would look like again same problem, maximize f equal to 3x1 plus 4x2, 7x1 plus 11x2 less than 88, 3x1 minus x2 less than equal to 12 and x1 greater than equal to 6, x2 greater than equal to 0. Now when we solve this particular problem, we get our solutions as for this part we get x1 equal to 5 and we get x2 as 4.8 and f star comes out to be 34.2. Now you see the problem with x1 star has been solved. It is an integer using the same simplex method that we learned earlier. On this side we will also get a solution, but this solution is going to be infeasible solution. You can try it yourself. No solution exists for this particular problem because satisfying this constraint and this constraint at same time is not possible for x to be greater than equal to 6 and x2 to be greater than equal to 0. So what we have done here is that we have pruned this particular branch. We have cut off the branch 2 and we will start with the branch 1. Now you see that this is going to be the lower bound on f star 34.2 and x1 equal to 5. Think about the polytop that we have been talking about. We have now cut off that particular polytop and there is no better solution that we can have when x1 is forced to be the integer. So this becomes our new seed to spawn other branches around y star and solve this particular problem. So now what we will do in next case, we will again work on making x2 as integer. Now understand that we will not settle for x1 equal to 5 as a final answer. We have just determined that when we force x1 to be integer, what is the best solution we can get? Since x2 does not happen to be integer, when we forced x1 to be integer, we have to still keep on spawning more and more branches until we convert every decision variable to be an integer. So what we will do? We will say that maximize f equal to 3x1 plus 4x2 subject to 7x1 plus 11x2 less than equal to 88, x1 less than equal to 5 because x1 equal to 5 is the maximum value to which you can stretch your constraint and we want to make it a feasible linear programming problem. So we will go with x1 less than equal to 5 and we will have x2 less than equal to 4. This is something that we borrowed from first branching that we did in earlier slide, and here I will just move it bit to the left. The second branch would be f equal to 3x1 plus 4x2 again subject to 7x1 plus 11x2 less than equal to 88. x1 still remains less than equal to 5, this is frozen, and x2 is greater than equal to 5. You again see x2 was some 4.2 in our original solution. So we will floor it, we will seal it and explore that on what side we should be pushing the solution. Now when we solve this, you would see that in one case we will get our x1 and x2. So if our x2 happens to be 4 and x1 happens to be 5, we get our solutions as 3 5s are 15 plus 16 is equal to 31. You can check it from Tableau. This is what you are going to get. Here I have just skipped the optimization step, but you can follow it from linear programming problem. And in this case, what I get x1 equal to 0 and x2 equal to 8, that would satisfy all the constraints and give me the value of 32. Now you see, among all the possible solutions in integer space, we got 31, we got 32. In previous slide, we got this particular answer as 34.2. However, there x2 was not feasible. So we will settle for our answer here that f star is equal to 32 because no further branching is needed. All the variables have reached their integral values, all the constraints are satisfied, but what we have done essentially is that we kept on pruning the polytop until we reach a wedge or a side where all variables happen to be integer now, and that terminates our integer programming exercise. Now this particular modules are certainly on the top of linear programming problems, and that is why getting good grasp of linear programming problems become very important when we talk about optimization. Now that we have learned this branch and bound method, you understood the name comes from branching and bounding to the floors and to the ceilings, but it is important to again go back that why it really matters in infrastructure, because in infrastructure most of the planning decisions are discrete, as a result of which fractional solutions from linear programming are invalid, and that is where branch and bound methods that incorporate this pruning the planes or using this analogy of cutting the plane until we get a smoother wedge along the integer works. And we can also explore other cutting plane methods, but broadly all these methods to solve integer programming belongs to the class of cutting plane problems until you reach the integer solution surface. So, key takeaways for us here is that this particular method does extend linear programming for discrete real world decisions, and that is the essence of our course on infrastructure decision making. And multiple fractional LP optima pose no problem. Branch and bound method just picks any fractional solution and branches. What we did for 2 variables, same thing can be done for 3 variables, 4 variables, n variables. Only thing is that number of branches will keep on increasing, but with the compute of today, this of course looks very intimidating that if we have 100 variables, you only have to now see it from the other side that you would only be spawning 100 times 200 branches for each variable, and ultimately you would hit the convergence very soon. So with the present days computational resources, this is not really a large number, but you get the solutions which are implementable in real world. And good thing is that with this systematic approach, it is guaranteed that we will always converge to an integer solution in fastest possible manner rather than searching for over the entire grid space in haphazard